PU2 champions, welcome to the first episode of Dhurandhar series. So children, in today's class, we are going to do the one-shot revision of the chapter Haloalkanes and Haloarenes. Okay, so in this particular video, we will be covering all the important reactions, all the important name reactions, mechanisms, polyhalogen compounds, and so on and so on. So if you watch this one video, the whole chapter will be done and you will be clear with all the concepts. So let's get started and see what we have in today's video. Before starting, do not forget to hit the subscribe button because this channel is going to be your ultimate solution for your KCET and PU2 2026 exams. So let's see what we have in today's class. So first we will talk about classification and nomenclature. Next we will discuss the nature of CX bond. After that we'll talk about how do we prepare haloalkanes. Next we'll talk about the preparation of haloarenes. After that we'll discuss the physical properties, chemical reactions of haloalkanes, and then we have chemical reactions of haloarenes, and lastly we'll talk about polyhalogen compounds. So my dear children, this pattern you have to remember for all the functional groups. You have to study their methods of preparation, then we have the physical properties, and then the chemical reaction. So if you understand that all the functional groups will be covered in this way, then you will have a clarity. Okay, so let's get started for nomenclature and classification. So how can we classify the hydrocarbons, or the haloalkanes? Okay, but before moving to the classification, let us understand what is haloalkanes. Okay, how do we define haloalkanes? So now whenever to any alkyl group, we denote R for alkyl group, you attach a X. X stands for halogen. Okay, then we call it as haloalkanes. And whenever to any AR, means to any benzene ring, if you attach a X group, that is a halogen, we call this type of compounds as haloarenes. So in this particular chapter, we are going to learn how these haloalkanes are prepared, how the haloarenes are prepared, and their reactions. Okay, so before starting about the reactions and all, let us first understand the classification of haloalkanes. Okay, so now see, the first basis of classification can be the number of halogen atoms. The second is the Sp3 C-X bond, means whenever you have this C-X bond, if this particular carbon is Sp3 hybridized, then what are the possibilities of classification? Next we will see if the carbon is Sp2 hybridized. Okay, the carbon which is containing the X group, if that is Sp2 hybridized, then what are the classifications we have? So first let's talk about on the basis of number of halogen atoms. This is very simple. You have to just check how many halogens atom are there in a particular compound. If you have one halogen just, then we will call it as a monohaloalkane. If you have two X groups, then it is a dihaloalkane. If you have three X group, then it is trihaloalkane. Similarly, in case of haloarenes, one X group, then it is monohaloarene. 2X group, then it is dihaloarene, and when you have 3X group, we call it as trihaloarene. Okay, now let's see the classification of Sp3 C-X bond. Now let me just tell you what is Sp3 C-X bond. So when you have carbon and that carbon is having X or it is attached to an X group, but this carbon is having 3 sigma bonds. Okay, if the carbon is having 3 sigma bonds, then we call this carbon is Sp3 hybridized. Okay, so now based on this Sp3 hybridized carbon, what all classifications we have? So the first one is we'll be talking about the alkyl halides, primary, secondary, and tertiary structure. Second, we'll talk about allylic halides, and third, we'll talk about benzylic halides. Okay, so let's first see about the first category of classification, that is primary, secondary, and tertiary. So remember, whenever the carbon which contains the X group, if it is attached to only one another carbon, okay, it is attached to only one another carbon, then it is a primary group. So for example, if I have CH3 CH2X, now see, this particular carbon which contains the X group is attached to only one carbon, so this is a primary haloalkane. Now secondary haloalkane means the carbon which contains the X group should be attached to two other carbons. So for example, if I draw a structure CH3 CH and CH3. Now see, this particular carbon which contains the X is attached to two other carbons, so it is a secondary carbon. Similarly, when you have a X attached to the carbon or carbon having X is attached to three other carbons, we call it a tertiary carbon. Okay, so this is how we can classify primary, secondary and tertiary carbons, and this is super important to understand because on this the reaction mechanisms depend a lot. Okay, so I hope all of you are very clear with how to identify primary, secondary and tertiary carbons. Next we'll talk about allylic halides. Now understand, this seems little bit complicated, but if you understand it is very simple. Now allylic means the carbon, suppose there is a double bonded carbon. Now the next carbon attached to this double bonded carbon is called as allylic carbon. Okay, please be clear here. The carbon which is attached, this carbon which is attached to a double bonded carbon. Okay, now this carbon is called allylic carbon, and if this carbon contains X, then we call it as allylic haloalkane or allylic halide. So you can see your example. Now see, this carbon is having double bond and this carbon is attached to the carbon having double bond and it contains the X group. So this is my allylic carbon. Next is benzylic halide. So benzylic means if the carbon which is attached to benzene ring, okay, that contains the X group, then we call it as a benzylic halides. Okay, clear? Now we will move to vinylic halides. Vinylic halides is simple for sp2 hybridization. So if the carbon is sp2 hybridized and it contains the X group, then we call it as vinylic halides. Similarly, this is also an example because this carbon here is sp2 hybridized. How to identify sp2 hybridized carbon? So you need to have two sigma, like this. You have 3 sigma bonds and you have 1 pi bond. Okay, then this particular structure is called as your vinylic halides. Next we'll talk about aryl halides. So when the X group is directly attached to the benzene ring, okay, when the X group is directly attached to the benzene ring, we call it as aryl halides. Okay, you can see example here, you can see example here. Clear? Okay, next let's discuss about the nomenclature. Okay, so nomenclature is very simple to your normal IUPAC rules, but yeah, common rules or common names are more important. You need to remember them. So first let's discuss some common names. So if you have a secondary chloride, okay, means any secondary carbon is containing Cl group and it is a 4 carbon compound, then the common name is sec-butyl chloride and IUPAC name is 2-chlorobutane. Now if you have like this particular structure like this, you have 3 carbons, oh just a minute, 1 second. So if you have a structure like this, you have 3 carbons here and then 4 carbon here, right? 1 here it is attached, then the next carbon, this carbon is containing the Br group. Okay, so this type of structure is called as neopentyl bromide or 2,2-dimethyl 1-bromo 2,2-dimethyl propane. Next, if you have tertiary carbon, then it is tert-butyl bromide and then we have 2-bromo 2-methyl pentane. Okay, similarly you can see this is vinyl chloride and this is allyl bromide. Okay, next if you have adjacent position, then we call it as orthochlorotoluene, and if you have benzyl chloride, then it is called chlorophenyl methane. Okay, now here there is something important. This particular structure is very important. Now I'll discuss two more structures, that is geminal halides, okay, and vicinal halides. Now see, if one particular carbon contains 2 X groups, like you have seen here CH2Cl2, then we call it as geminal dihalides. Okay, geminal dihalides. And how is their common name written? Methylene chloride. Okay, the common name will be alkylene. 1 second. Yeah, alkylene chloride. Or here you can say methylene chloride. Or next, vicinal chloride is when you have 2 adjacent carbons and they have X groups. Okay, and these type of compounds are called as vicinal dihalides. Okay, and their common name is like ethylene dichloride or ethylene dihalide. Okay, ethylene dihalide. So these two you should remember. Now let's move to the nature of CX bond. This is very simple. See, C and X is there. We know X is more electronegative, so it will pull the electron towards itself. So here we'll have a delta negative charge and here we'll have a delta positive charge. So that is why this bond is a polar bond. Okay, now since this carbon is having a positive charge, it is electrophilic in nature. So whatever nucleophiles come, okay, it can directly attack on the carbon. Okay, so why is the polar nature is there? That is due to the electronegative nature of the halogen atom. Next, charge separation. The carbon has a positive charge and the halogen have a negative charge because of the electronegativity of the halogen. Next, the bond strength decreases down the group. So if you see, as the size is increasing, the bond strength decreases. So CF is having higher bond, then CCl, then CBr, and Ci is having the least bond enthalpy. The polarity is the root cause of nucleophilic substitution reaction. Because of this polarity only, the carbon is having a delta positive charge and it acts as an electrophilic center. Clear? Now we will move to the preparation of haloalkanes. Okay, this is very important and I want all of you to draw this schematic diagram and to understand, to have a clear picture of what are the different methods by which we can prepare haloalkanes. Okay, so let me explain you this diagram. So preparation of haloalkanes we can do from three major sources. The first one is alcohols, second one is from hydrocarbons, and the third one is the halogen exchange method. Okay, now from hydrocarbons, again we can further divide it from from alkanes and from alkenes. Now from alkenes we can further divide it into addition of HX and addition of X2. Okay, let me just repeat it and I want all of you to just pause the video here, see this diagram and then recall yourself. Okay, then only see, organic chemistry consists of a lot of reactions. If you just keep on recalling, if you draw such diagram based I can say mind maps, that will help you to remember better. So let's just pause this video. If you have already noted down, close your notebooks and try to recall. Preparation of haloalkanes. We have three methods. The first one is from alcohols. Second one is from hydrocarbons. Third one is under halogen exchange method. Now from hydrocarbons we have two methods. One is from alkanes and from alkenes. Now again from alkenes we have two methods, that is from addition of HX and addition of X2. Right? And then the halogen exchange method has two methods, that is Swartz reaction and Finkelstein reaction, about which we are going to study in detail. Okay, so let's start with from alcohols method. So from alcohols, if you see, one second. So if you see from alcohols, the first reagent that we can use is HCl and ZnCl2. This one will give me RCl plus H2O. Okay. Next, for addition of bromine, you can use NaBr plus H2SO4. This will give you RBr plus NaHSO4 plus H2O. Now, in these two reactions, the byproducts are not important. The main products are important. But here, PX3 and PCl5, here the byproducts are very, very important. So you can use either PCl3 or PBr3. You will get 3Rx plus H3PO3. And if you use PCl5, then we'll get RCl plus POCl3 plus HCl. Okay. Next, the fifth one is red phosphorus and X2, and here you will get Rx. And the sixth one is SOCl2, where you will get RCl plus SO2 plus HCl. Now, this particular reagent is called as thionyl chloride. Thionyl chloride. Okay. Now, here one very important thing that you should note, that this thionyl chloride, right? This thionyl chloride is the best method for preparation. Okay, this question has been asked repeatedly, that why this thionyl chloride is the best method. Okay, this is the best method because here this you can see the byproducts. What are the byproducts? We have SO2 and we have HCl, right? Both the byproducts are gaseous in nature, right? So what will happen? They will simply evaporate. Okay, and if they will evaporate in the container or in your sample, you just have pure RCl. You do not have to do any purification method, any separation method to obtain the product, right? So directly you will get your product in the purest form, and that's the reason why this is the best method. Okay, moving forward. So from alcohols, how many reagents we have? 6. So just again take a pause and recall. HCl and ZnCl2, NaBr and H2SO4, PX3, PCl5, then we had H2 red X2 red phosphorus, and lastly SOCl2. Okay, now we'll move to from hydrocarbons, and the first one we'll discuss is from alkanes. Okay, so here the mechanism that is followed in alkanes is free radical halogenation. Okay, so this is a method of free radicals. So here in this process, free radicals are formed. Now the reagent used here is chlorine or any bromine you can use in presence of UV light or heat. So here what happens, every possible hydrogen can get replaced and you will get a mixture of products. Okay, you will get a mixture of products. So now if you see here, you can get, if this hydrogen is replaced, you will get 1 chlorobutane, and if this hydrogen is replaced, you will get 2 chlorobutane. So you will get a mixture of 1 chloro and 2 chlorobutane, right? And so that is why this is not a preferred method. Okay, why? Again, the same reason or the opposite of the previous one you can discuss, that this is not a preferred method because here we get a mixture of products, right? We have to separate them. We need to, suppose I want only 1 chlorobutane, but in this method also 2 chlorobutane will be produced. So you have to do a lot of after preparation techniques has to be done to get the pure sample. Okay, so that is why this is not a preferred method. Moving to the next one, that is from alkenes, and the first one here is the addition of HX. Okay, now addition of HX, remember, follows Markovnikov's rule. Okay, Markovnikov's rule. Now what does this tells you? This rule tells that in HX the negative part, means the X minus, will go to the carbon with less number of hydrogen. Will go to the carbon with less number of hydrogen. Okay, now let me give you an example. Suppose I have propene, okay, CH3 CH double bond CH2, and I'm adding here HBr. Okay, so what will happen? This double bond will break and you will have 2 single bonds instead of that. Okay, so you have CH2, here one bond will be attached and here one bond will be attached. Now the question arises, to which carbon bromine will be attached and to which carbon hydrogen will attach. So for that we have this Markovnikov's rule, which says that the negative part, means this X, will go to the carbon with less number of hydrogen. So if you see, this particular carbon is having 1 hydrogen and this carbon is having 2 hydrogen. So the negative part will go to the carbon with less number of hydrogen. So Br will attach here and H will attach here. Okay. Now there is another parallel rule to this, which is called as anti-Markovnikov's rule. Which is called as anti-Markovnikov's rule. Okay, now it is, if you can just see here, Markovnikov's rule will that X minus will go to the carbon with less number of hydrogen, then here X minus will go to the carbon with more number of hydrogen. Okay, now when can we use anti-Markovnikov's rule, or what is the reagent for using anti-Markovnikov's rule? So remember here, the only reagent which can follow anti-Markovnikov's rule is HBr with peroxide. Okay, you cannot have HCl, HF, HI, nothing, only HBr with peroxide. So if this propane is there and if I add here HBr with peroxide, okay, so what will happen? Just the opposite will happen, and the bromine will go to the carbon with more number of hydrogen, right? So here 2 hydrogen is there, here 1 hydrogen is there, so negative part will attach here and I will get a compound like this. Okay, so this is the product. Now you can see with the same reactant and just by addition of 1 peroxide, we can get 2 different products. Okay, so please keep this in mind. Okay, moving forward, from alkenes only, addition of X2. So if you have an alkene and if you use this particular reagent, that is Br2 with CCl4, the double bond will break and to both the carbons you will have bromine attached. Okay, and this is, you can see adjacent carbons are having halogens, so we call it as vicinal bromides. Moving to the next one, that is halogen exchange method, the third method for preparation of haloalkenes. So here what happens, halogen exchange method, here the starting materials are haloalkenes, but we get different haloalkenes as the product. So mainly we have Finkelstein reaction, which is present for the preparation of iodoalkenes. Okay, so what you take, Rx, X can be Cl or Br here, and treat it with NaI, and here we have a reagent that is dry acetone. Okay, so you take NaI, treat it with dry acetone and you will get Ri plus NaX. Okay, next we have Schwarz reaction. So here what we can have, Schwarz reaction is for the preparation of fluoroalkanes. Okay, so you have any haloalkane and you treat it with metallic fluorides. So what all metallic fluorides we can use? AgF, Hg2F2, COF2 or SbF3. Okay, so these all metallic fluorides can be used here, and this bromine can be replaced with fluorine by producing AgBr. Okay, so these are 2 methods by which we can produce iodoalkanes and fluoroalkanes. Clear? So with this we are done with the preparation of haloalkanes. Now let's move to the preparation of haloarenes. So for preparation of haloarenes we have 2 main sources. Okay, the first one is our from hydrocarbons and the second one is from amines. Okay, from hydrocarbons you have already studied this reaction, I think, in the lower classes. So let's see. So what we can do is electrophilic reactions to benzene or substituted benzene. So if you take X2 with Fe dark, okay, then what will happen, this X will be attached at ortho position and at para position. Okay, so you can have ortho halotoluene and you can have para halotoluene. Okay, now let me just tell you that the major product is definitely the para one. Clear? Now the next method of preparation is your Sandmeyer reaction from amines. Okay, so first what we do is to take amines, or which is also called as your aniline. Okay, now benzene with a amine group is called as aniline. You take this one and treat it with NaNO2 and HX. Now remember, this is nitrous acid and can sometimes also be written as HNO2 in the question. This converts this amine to benzene diazonium halide. Okay, so if you are taking chlorine, then benzene diazonium chloride. Now once this product is formed, this is a very important product and a very unstable product, but yes, from this we can prepare many other products. So this benzene diazonium chloride can react with Cu2X2, where this X, now what will happen, this N2 will go out and then this X will attach. With nitrogen gas as a byproduct, you can treat this and you can get chlorobenzene or bromobenzene. Okay, then but from the same product, if you want to get iodobenzene, you can also treat it with Ki, and then what will happen, N2 gas will go and your I will be attached here. Okay, and N2 gas is released. So this is also a part of Sandmeyer reaction. Okay, so you have to use copper salts of halides for chloro and bromobenzene, and you can use Ki to get iodobenzene, right? So with this we are done with the preparation of haloarenes. Clear? Okay, now let's talk about their physical properties. Okay, so see, physical properties is very important. The first factor is melting point. Remember, always when the mass will increase, the melting point will increase. Okay, so when mass increases, what happens, the van der Waals forces increases. Okay, the van der Waals forces increases. Okay, and the intermolecular forces also increase because of that, and the boiling point increases. Next, it decreases with the increase in branching. So if the branching is more, then the boiling point or melting point will decrease. Now let me give you an example. Suppose we have here so normal butane is there, okay, like one halobutane, and you have another structure like this. Okay, now see, okay, just a minute, I'll make branching here first. Okay, now see, here if you see, this is a straight chain, this is a branch chain. So always the straight chain boiling point or melting point will be more than branch chain. The reason being, when it is a straight chain, it is very easy to pack the molecules, they can be tightly packed with each other. But when you have branching, there's a lot of empty spaces and the packaging of the molecules is not tight. Clear? Moving to density, so as the mass will increase or the number of carbon increases, the density will also increase. The solubility, they are less soluble in water but more soluble in organic solvent. Solubility decreases with the increase in mass. So as the R group, okay, this is there, right? As the R group increases, the solubility will decrease. Okay. So now let's talk about the chemical reactions of haloalkanes. Okay, this is very important. Now see, haloalkanes can show you three types of chemical reaction. The first one is nucleophilic reactions. This is because we have already discussed in the nature of C-X bond, right? The C is electrophilic in nature. So that is why nucleophile can easily attack on C. Next, we'll talk about elimination reaction, and lastly, we'll talk about reactions with metals. Okay, so let's start with nucleophilic reactions. So under nucleophilic reactions, we will see what are the types of nucleophiles that can attack. Then we'll talk about the mechanisms of nucleophilic reactions, and then we'll also talk about the stereochemical aspects of the nucleophilic reactions. So let's start with the type of nucleophile. See, any like you have this particular structure, right? One second. Just a minute. Yeah. So you have this Rx, and when this nucleophile attacks, okay, you will get RNU. Okay. So now what are the different nucleophiles that are possible? So let's see. If you use NaOH as a reagent, it will give you nucleophile OH minus, and what will be the product? In this place of Nu, I will add ROH, which is an alcohol. Similarly, if you use water as a reagent, H2O is a nucleophile, and that will also attack on this R, and you will get alcohol. Similarly, you can have NaOR as a reagent that will give you RO minus as a nucleophile, and this can attack on R to give you ROR dash or ether. Next, if I use NaI, that will be I minus, and this I minus will attack on R and I'll get alkyl iodide. Next, NH3 we have, and this is also nucleophile is NH3, and you will get RNH2, which is a primary amine. Next, we have R dash NH2. R dash NH2 will be attacking on this one, and you have RNH R dash, and this is secondary amine. Okay. Similarly, you can see, but these two reagents are very, very important. For KCN, if you use, you will get CN minus nucleophile, and the product you will get is RCN, which is nitrite. And on the other hand, if you have AgCN, it will have the nucleophile is itself AgCN, and you will get the product RNC. Okay, and this is isonitrite. Next, if you have KNO2, so here the nucleophile is ONO. Okay, and you will get RONO, which is alkyl nitrite. Next, if you have AgNO2, you have AgONO, and that is RNO2, and you will get nitroalkane. Now, similarly, if you have RCOOAg, the nucleophile is RCOO minus, and you will get the product R-C double bond OR, which is an ester. LiLH4 will give you a nucleophile H, and you will get the product RH, which is simple hydrocarbon. Next, if you have Grignard reagent R minus MgX, R minus is the nucleophile, and R will form, which is the alkane group. Clear? Now let's talk about the mechanism. So we have two mechanisms, one is SN1 and another is SN2 mechanism. Now what happens in SN1 mechanism? Now see, SN1 is a two-step mechanism. The reaction takes place in two steps. The first step is the formation of carbocation. Okay, you can see here the structure actually looks like this. You have CH3, CH3, CH3 and Br. So at first what happens, this group leaves and you get a carbocation. Now what is the speciality of this carbocation? This is a planar molecule, okay, and the carbon here is now Sp2 hybridized. Now what will happen in the step 2, this Br minus or any nucleophile will attack, okay, and you will get the product here. Clear? Now the point here is the nucleophile, this is now a planar molecule. Okay, you can see this particular is a planar molecule, and the OH minus can attack from the top side and can also attack from the bottom side. Okay, the relevance of this we will understand when we study the stereochemical aspects. Clear? Okay, now let's see some points about this. So first of all, it is SN1 reaction. It follows first order kinetics. So you see when if you have studied chemical kinetics, you might be knowing that the slowest step is the rate determining step, and the step 1 here is the slowest step. Okay, so if this is the slowest step, and you see in this slowest step I have only the reagent, there is no role of nucleophile in the first step. So that is why the rate determining step or the rate of the reaction is only the first order kinetics and depends only on the concentration of alkyl halide. Clear? Then what is the steps involved? It occurs in two steps. First is the formation of carbocation, second is the attack of nucleophile. Solvent preference. So since there is a carbocation formed here, the reaction is generally more stable in polar protic solvents like water, alcohol or acetic acid. Next, the stability of carbocation, faster will be the reaction. So the order is 3 degree, 2 degree and 1 degree. Next, special cases, even allylic and benzylic halides are stable because of resonance. So they will also show SN1 reaction. Then reactivity order. So now see, the first step is the breaking of the leaving group. So if the bond is weak, it can easily leave and the reaction can be faster. So we have Ri, Rbr, Rcl and Rf. So Ri, I can break easily and this reaction will be the fastest one. Clear? Now let's talk about SN2 mechanism. Now SN2 mechanism occurs in one step. Okay, this is a one-step reaction. So here what happens, you have, for example, this is the leaving group, okay, and this is the nucleophile. Now what will happen? The nucleophile will attack from the back side, okay, and you will have a structure like this formed, okay, and this structure is called as transition state. Okay, now when you have this transition state, this bond will form and this bond will break. Okay, so this will be the final product that is formed. Now what do you observe here? Now see, the nucleophile which is attacking is on the opposite side of the leaving group. Okay, the nucleophile is always on the opposite side of the leaving group. Okay, now the importance of this also we will understand in the stereochemical aspects part. So first of all, let's see one example. Suppose this is a reactant, OH minus will attack here and you can see that this is a transition state formed where the carbon is having 5 bonds, then this bond will form and this bond will break and you get the chlorine out. And you can see here that the OH is on the opposite side of chlorine. Now let's see some points on SN2 mechanism. So first of all, it is SN2 reaction. Kinetics here is a second order kinetics. Now why it is a second order? Now see, there's only one step in the reaction. And in the beginning only, both the Rx, that is the substrate, and the nucleophile, both are involved in the reaction. So that is why the reaction rate will depend on nucleophile as well as on alkyl halides. So that is why it is a second order reaction. Next, how many steps are involved? It is a single step reaction. Transition state. Okay, so you can see that there is no intermediate formed, but a transition state is formed where the carbon has 5 bonds. Okay. Next, the carbon structure in the transition state, all the CH bonds lie in the same plane during the transition state. Next, you can see that actually what happens here is, see, the when the reagent attacks, okay, after that the product formed, you can see that it is completely inverted. At the starting, chlorine was on this side, okay, you can see this is the holo and chlorine is on this side, and at the end you will see this has become like this and this side it is the OH. So there is like an umbrella has I can say umbrella has turned upside down. Okay, it is like inversion like that. So like an umbrella in a strong wind. So this is also called as Walden inversion. Okay. And what is the order of the reaction? So since the nucleophile has to attack when already the living group is there, so if there is more steric hindrance, the reaction will be slower. So lesser the steric hindrance, faster is the SN2 mechanism, and that is why the order here is 1 degree, 2 degree and 3 degree. For SN1, the criteria was the stability of carbocation, because there in the first step carbocation was formed. So stable the carbocation, faster will be the reaction. So that is why there the order was 3 degree, 2 degree and 1 degree. Okay. Next, we'll talk about the stereochemical aspects. Okay, this is very, very important. So before understanding stereochemical aspects, we need to understand certain terms that is very relevant here. The first one is optical activity. What do you mean by optical activity? Now see, if any sample is there, okay, and you are passing a plain polarized light here. Now ma'am, what is this plain polarized light? Okay, let us understand that also. See, a light is an electromagnetic wave, right? A light has many fields, but when you pass this light through a polarizer, okay, then you will have a light which is having only one field. It can be any field, but if a light is having only one field, okay, in any one direction the fields are present, then we call it as a plain polarized light. Now when your light passes through any sample, and after passing through the sample, if the light is rotated, okay, to clockwise or anti-clockwise direction, so if any sample is able to rotate the plain polarized light, then we call that sample as optically active. Okay, so what do you mean by optically active sample? So any compound which is having the potential or which can rotate the plain polarized light is called as an optically active compound. Okay, now ma'am, how to know that whether it is optically active or not? Do we have to go to the lab and put the sample every time and check that, okay, whether the light is rotated or not? No, you don't have to do like that. We have a shortcut for this. So that shortcut comes with the understanding of chirality. So now see, if any compound is having if any carbon is having 4 different groups, okay, then that carbon is called as chiral carbon. Okay, and if in a compound there is a chiral carbon, then there is a chance that that molecule will be optically active. Okay, got it? What's the point here? If any what is chiral carbon? A compound which has a carbon which has 4 different groups attached. So if in a molecule there is one carbon which is having 4 different groups attached, then definitely that molecule is optically active and it can rotate the plain polarized light. Okay, now let's talk about something called as enantiomers. To understand this, let us take one example. Suppose I have a compound like this. Okay, now see, this particular compound, just check and tell me whether this particular compound is optically active or not. So for that, what is the criteria? You need to check if there is any chiral carbon or not, or a carbon which is having 4 different groups attached. Now if I see this particular carbon, okay, you can see here I have hydrogen, here I have methyl, here I have Cl and here I have ethyl. Yes, this carbon is having 4 different groups. So that means this is a chiral carbon, and if it is a chiral carbon, this molecule is what? Optically active. Okay, right? This molecule is optically active. Now, if this molecule is optically active, then what it will do? It will rotate the plane polarized light, right? Now, if this is rotating the plane polarized light, now there is a two conditions of rotation of plane polarized light. You can either rotate the PPL, I'm writing PPL for plane polarized light. You can either rotate it in clockwise direction or you rotate it in anti-clockwise direction. Now, for example, suppose this molecule rotate in clockwise direction. So for clockwise direction, we denote this particular compound as small d or with a plus symbol, which says that this compound is rotating it in clockwise direction. Now see, you cannot just see a molecule and tell whether it is rotating clockwise or anti-clockwise. This has to be done experimentally. Okay. Now if this compound is rotating the light in plus or in clockwise direction, there has to exist a molecule of similar to this one, or I can just use the direct word, there will be an existing a mirror image of this molecule. Okay, mirror image, non superimposable. Okay, so they need to have a non superimposable image of this compound which will rotate the light in anti-clockwise or in levorotatory. Okay, so if it is plus clockwise, it is called dextrorotatory. So this small d stands for dextrorotatory, okay, and this small n stands for levorotatory. Okay, so now see, first of all, if a molecule is having a chiral carbon, that means it is optically active. If the molecule is optically active, it will rotate the plane polarized light. Now, if the light is rotated in clockwise direction, then that particular compound will have its non-superimposable mirror image, which will rotate it in anti-clockwise direction. So now this particular compound and its non-superimposable mirror images are called as enantiomers. Okay. Now, ma'am, what is this non-superimposable mirror image? Now, see, suppose I have a letter A. I'll draw its mirror image. It will come A. Now, you can take this A, and if you put on the original one, it will exactly superimpose, right? It will exactly overlap. These are called as superimposable mirror images. But if I take a letter B, for example, okay, now if I draw its mirror image, and if I bring this one and keep on this one, how it will look? This will be like this and this will be like this. So it will not be exactly overlapping, or this is called as non-superimposable mirror images. So what do we understand now? If a molecule is optically active, it will have a non-superimposable mirror image, and both of them will, one will rotate in clockwise, the other one will rotate it in anti-clockwise, and these two compounds or these pairs are called as enantiomers. So how we will define enantiomers? I hope you have noted it down, because I am going to write down the definition of enantiomers now. So enantiomers are non-superimposable mirror images of each other, okay. Enantiomers are optically active non-superimposable mirror images of each other. Now see, these enantiomers have all the properties same, okay. Their boiling point, melting point, their density, their weight, their mass, everything is same, okay. Their all the physical properties are same, okay. All physical properties are same. But there is one physical property which is different, and that one physical property which is different is the direction of rotation of plane polarized light, okay. So if one is rotating in clockwise, the other one will rotate it in anti-clockwise direction, and these two pairs are called as enantiomers, okay. Now let's understand what is the use of the stereochemical aspect in our SN1 and SN2 mechanism. So let's first understand for SN1 mechanism, okay. Now see, okay, 1 second, just a minute. Yes. Now see, in SN1 what happens, you know, the first step is what? There's a formation of carbocation. Now you see this particular compound is having methyl group, ethyl group, hydrogen and bromine. So this carbon is chiral compound. So this particular compound is optically active, Okay, now when this bromine is lost, you get a carbocation. Now this is a planar molecule. Now the nucleophile can attack from both the sides, upside also, downside also. So if OH minus is attacking from the top side, okay, so for example you're getting a product here, and if you're getting the OH minus on the bottom side and you are getting a product like this. Now suppose, let us assume that this particular compound was minus, okay, means it is a levorotatory, suppose. But the product that you will get both the products. You will get dextrorotatory also, levorotatory also in equal amounts. Okay, so because why? Because the OH minus can attack from both the sides and you can get both the products. Now see, if you are getting if the OH is on the opposite side of Br, as in this one, then we call it as inverted product. Okay, now if the OH is on the same side of Br, then it is called retention. Okay, because in this what will happen, if it will retain the direction of rotation. If this was anti-clockwise, this one will also be anti-clockwise, and inverted, this one will be clockwise. Okay, so now what we have understood, there is a term that is very important here, which is your racemic mixture. Okay, so now SN1 mechanism gives you racemic mixture. Now what is racemic mixture? It is a mixture which contains equal proportions, okay, which contains equal proportions for both the enantiomers. Okay, which contains equal proportions of both enantiomers, means your plus and minus will be produced in equal amounts. Now if I take this particular sample, okay, so just imagine now you have taken this particular sample, you have added plain polarized light, okay, and you have taken here, added both of them, that is this reactant you have added. So I'm just denoting it with R so that I can write here. So if you have added R and then OH minus, okay, you have mixed in this sample. After some time, when the reaction has taken place, what you will observe, that there will be both the samples D and L in equal amount. So now this contains a racemic mixture. So what will happen? The plain polarized light, if one enantiomer is turning it to left, the other one will will turn it to the right. So at the end, the net effect is zero, and you will find the light, the plain polarized light, remains unrotated, okay, or unchanged. So I can say that this racemic mixture is optically inactive now. Okay, why? Because it is not able to change the direction of light. Okay, now why it is not able to change the direction of light? Because two enantiomers are present in equal proportions. So children, this is important. If you have understood, please do let me know in the comment section that understood. Okay, if you have any doubt, just put down your comments. I have explained in a very simple way, but still if you don't understand, do let me know. Now let's move to the SN2 mechanism and stereochemical aspects there. Now see, if you see this particular compound, this is also a chiral carbon, and in SN2 what happens, the OH minus always attacks from the backside, right? So what will happen, if suppose this compound was positive, or if it was clockwise rotation, the other one, the product here, will be always levorotatory. It will be inverted configuration. Okay, so that is why in SN1 we always get inversion, whereas in SN2 we always get inversion, whereas in SN1 you can get both inversion and retention, and the mixture is called as a racemic mixture. Here you will get only one product. Okay, if this is D, the product will be L. If this is L, the product will be D. I hope this is clear. Now let's move to the next reaction, that is elimination reaction. So in elimination reaction, what happens if there is an beta hydrogen? Now what is beta hydrogen? See, the carbon which contains the X group is called the alpha carbon. The adjacent carbons are called as beta carbon, and the hydrogen attached to them is called as beta hydrogen. Now when the base is there and it accepts the hydrogen, and this bond comes here and the X goes, we get an alkene. So in elimination reaction, we get alkene as the major product. Okay, and then we have this BH, and then we have this X minus. Okay, so this is called as your final product, and here X is a living group. Okay, now there is one rule here to identify the product. That rule is called as Saidzev rule. Okay, so we need to understand that before seeing the example. Now this Saidzev rule tells us that if we have a reaction, okay, if we have an elimination reaction, then what will happen is the more stable alkene is formed. Okay, more stable alkene is formed. Now what I mean by more stable alkene is formed, that means if you see one alkene, okay, it will have 4 bonds like beside them. So if the besides of this one, okay, if it is more R groups, okay, if there is more R group, then it is more stable. Okay, let us understand this with an example. So for example, you have a compound 2-bromopentane. Okay, now you see this is my alpha carbon which is containing the halogen, and the next carbon here is beta, and the next carbon here is beta. So this hydrogen is beta hydrogen, and this hydrogen is also beta hydrogen. So now what will happen with OH and H? What will happen? You will see that there will be a double bond here. If I remove this H and this Br, you will get a double bond here, which is this one. And if I remove this H and Br, I'll get a double bond here. Okay, now let's see which is more stable. Now see, for the first one, if you have like this, okay, this side you have CH2 CH3, this side I have H, this side also I have H, and then I have CH3. Now see, around the double bond you have 2 carbons and 2 hydrogens, right? Now let's talk about this one. Here I have CH double bond CH2, and here I have CC something. Now if you see around this double bond, you have 1 carbon which is directly attached and 3 hydrogen. So what the rule says, if there is more R group, it is more stable, right? So here you can see there are 2 carbon, here I have 1 carbon. So this is definitely more substituted or more stable. So as a result of which you can see this one is formed in 81%, whereas this one is just formed in 19%. Clear? Okay. Next we'll talk about reaction with metals. Okay. So if you have any Rx, okay, and you treat it with Mg, then we get a special reagent called as RMgBr, which is your Grignard reagent. Okay, this is, just remember its preparation because we are going to use this much more in the upcoming chapters. Next is Woods reaction. So if you have Rx and you treat it with Na, and here we have to use dry ether. So what will happen? R product will form and NaX is the byproduct. I'll give you one example here. So if I have CH3 Cl 2 times plus 2 Na, then what I'll get the product with dry ether? CH3 CH3 plus 2 NaCl. Okay. So with this we are done with the reactions of haloalkanes. Now let's talk about the reactions of haloarenes. Okay. Now see, haloarenes will also show type of reactions like nucleophilic reactions, electrophilic reactions, and reactions with metal. Now first seeing the nucleophilic reaction. See, in haloarenes, the nucleophilic reactions is generally slower, or the haloarenes are less reactive towards the nucleophilic reactions. What is the reason behind it? Let's understand. There are 3 reasons, and these 3 reasons can be easily asked as a 3-marker question. Very, very important. Now see, the first thing is the resonance effect. When you have this Rx, okay, now this X is having lone pair which can undergo resonance, right? So there is a formation of partial double bond character. Now due to this partial double bond character, it is very difficult for the nucleophile to come, attack, and to throw out X, because here it is bonded with the carbon with a double bond, right? The double bonds are much more stronger. So that is why this reaction, the resonance effect reduces the chances of nucleophilic attack. The second one is the hybridization of this Sp2 carbon. Now see, the carbon to which the X is attached is Sp2 carbon. Now Sp2 carbon can hold, because it is highly electronegative, it holds the X very tightly as compared to your normal aliphatic one where this is an Sp3 hybridized. Okay. Next, instability of phenyl cation. So suppose if this X leaves, then what will be the byproduct, the remaining that will we have? That is this phenyl carbocation, which is highly unstable. Okay. So these are the reasons why the haloarenes does not show nucleophilic reactions. But does that mean there is no way that we can have haloarenes reactions? No, it is not like that. We can have haloarenes reaction if we decrease the electron density of the ring. Okay. Now for example, see, if you have this Cl and chlorobenzene, you are reacting it with NaOH and 623 Kelvin at 300 atm, you have to take such a high temperature and pressure. But if you add one NO2 group, the reaction can be done at 443 Kelvin. If you do 2 NO2 groups, you can do it at 368 Kelvin. And if you have 3 NO2 groups, then you can do it at only with warm water. So what is the point here? Why on adding electron withdrawing groups, the reaction rate increases? Now see, this is very simple. what happens here is, see, benzene, if you see the structure of benzene, it has this pi electrons, right? And if you just imagine the structure, it is like this. Here on the top we have electron cloud, and at the bottom we have electron cloud. Okay, now this nucleophile, okay, this is also electron rich, benzene is also electron rich, so there is a repulsion between the electron cloud of benzene and the nucleophile, because of which the reaction is also further reduced. So if somehow we can reduce the electron cloud of benzene by adding electron withdrawing groups, then what will happen? Then the reaction can be done faster, because this nucleophile can attack here. Clear? Okay, next we'll see the electrophilic substitution reaction. So these are basic reactions. So the first one we have here is halogenation. Okay, so for halogenation, what is the reagent we have to use? Cl2 and FeCl3. Now remember, X is an electron donating group, so it will have ortho para directing group. So chlorine with FeCl3 will add chlorine at ortho and para position. Okay, next if you take nitration, okay, concentrated HNO3 and concentrated H2SO4, so that will add NO2 at ortho and para position. Third, we have sulfonation. Okay, you have to just use concentrated H2SO4, so that will add SO3H at the, okay, here slight mistake, just a minute. Yeah, you will get one para product and you will get one ortho product. Okay, then fourth one is your Friedel-Crafts acylation. Here you will have COCH3 group attached at ortho and para position. Similarly, we can have Friedel-Crafts alkylation, CH3Cl-AlCl3. It will give you CH3 at ortho and para position. Okay, so these are the 5 reactions that are electrophilic reactions for the benzene ring or haloarenes. Now the third category of reaction is the reactions with metal. So this is very similar to your Woods reaction. In Fittig reaction, what we do, we take ARX, means a haloarene, and you treat it with sodium and dry ether, you will get diphenyl. Okay, and the product here is NaX, byproduct is NaX. Now see, what was Woods reaction? Woods reaction was Rx, and what was Fittig reaction? ARX. Now if I have Woods Fittig reaction, so you have to take one Rx and one ARX. So you have to take one haloalkane and one haloarene in presence of sodium dry ether. You will get a compound like this plus NaX. Clear? Okay. So this is all about the reactions with metals. So now with this we have completed the preparation of haloalkanes, haloarenes, chemical properties or reactions of haloalkanes and haloarenes. Now we will talk about some polyhalogen compounds that we have in our syllabus. Now these are polyhalogen compounds, means you will have more than one halogen in a particular compound. So we will be basically studying about their uses and their harmful effects. Okay, so the first one we'll be studying about is dichloromethane, trichloromethane, and then we have triiodomethane, tetrachloromethane, freons and DDT. Okay, so let's start with dichloromethane. So basically you just need to remember their uses and their harmful effects. So they are mainly used as paint remover, propellant, and they're also used as a solvent. Okay, now what are their harmful effects? At lower level they can cause impairing in hearing and vision. At higher level, dizziness and nausea. Direct skin contact can even burn your skin and can even burn your cornea with direct contact. Okay, so these are the harmful effects. Next is your trichloromethane. Trichloromethane means CHCl3. Okay, this is also called as chloroform. Okay, now it is used as a solvent. It is also used in the manufacture of refrigerant R22. Okay, harmful effects: nervous system, it causes dizziness, damage liver, kidney, direct skin contact, it can cause burning. And what happens is this chloroform, right, when it is left open or when it can oxidize, it produces COCl2, which is a very poisonous gas, and we call it a phosgene. Okay, and HCl. So that is why what we do is chloroform is always stored in dark bottles. Okay, so where there is no light, and this reaction can be prevented. Okay, next one is triiodomethane. Again the formula here is CHI3, and here what we see, so it is used as an antiseptic. It was earlier used, but the antiseptic property is not because of this iodine, but when it is used it produces free iodine, that is I2, which can cause the healing and can be used as an antiseptic agent. Next we have tetrachloromethane, that is CCl4. Okay, it is used in the manufacture of refrigerants and aerosol cans. Lower level, it causes dizziness. Higher level, it can cause even coma. Direct skin contact can cause burning, and environmental pollutant, it causes depletion in the ozone layer. Okay. Next, this is very important from exam point of view, freons. The compounds or the chlorofluorocarbons of methane and ethane are called as freons. Okay. So when a compound you have chlorine as well as fluorine, then we call it a chlorofluorocarbon. Okay, so here there's a small mistake. Freon 12 is CCl2F2. Okay, you have chlorine and fluorine, and it is prepared by using Schwartz reaction. Okay, what are its uses? Aerosol, refrigeration, air conditioning, and harmful effect. Definitely you might have studied. These chlorofluorocarbons are the main source of ozone depletion and can cause global warming in the long run. Okay. Next, we'll talk about the last compound, that is DDT. Okay, so the chemically, so this is actually the first, I can say, man-made insecticide. Okay, DDT. The problem here is it is not biodegradable. It is not metabolized by animals. Instead, it is deposited and stored in their fatty tissues. And if ingestion continues, DDT builds up within the animal over time and can cause harmful effects. So that is why DDT was banned in many of the countries, and now it is not used, but earlier it was used as an insecticide. It is also called as the first synthesized insecticide. You can see the structure here. You can also, this can be asked in the exam, so just remember the structure also. Okay, so children, yes, with this we have completed the chapter. I want all of you to just make the short notes of the reactions and just go through them, and next video I'll be coming up with the most important questions from this particular chapter, that is haloalkanes and haloarenes. Okay, so if you have any doubt, do not hesitate and put down your doubts in the comment section. I'll reply to all of them. And hit the subscribe button, because this channel is going to be your ultimate guidance for your preparation for KCET and PU2 2026. Okay, so all the best, my dear children, and keep learning, keep shining, and all the best.